Okay, I think we'll get started. So welcome to this mini course on rigorous chemical thermodynamics. I hope that if you are interested in thermodynamics and have a little bit of curiosity as to why some of the things that you perhaps learned in physical chemistry or thermal physics, and then going even way back to general chemistry, and you're a little bit curious about what are the real rigorous underpinnings. Hopefully this short course, including this lecture, 7 lectures on this, with a focus on getting to the important functions associated with chemical equilibrium. Before I jump into some of the context for the course, I'll just tell you who I am. So I'm Darren Olness. I'm a professor of chemistry at Concordia College, and I've taught chemistry and physics and a little bit of physical neuroscience during my career, my 25 years at Concordia College. This set of lectures is part of something that I'm putting together on YouTube called the GNL Project, and this is inspired by a quote by G.N. Lewis and really a motto by which I live out my scientific life, and that is physical chemistry is everything that's interesting. And it gives us an enormous amount of freedom to study what we want to study and look at the world through the eyes of and the context of physical chemistry. And so it just feels good to know how things work. And physical chemistry and how we learn physical chemistry really cuts to that. And so the purpose, again, of this course is to go through in a little bit more rigorous way. So this would be, I would call this, a more advanced course than just a regular undergraduate physical chemistry course. So this would be after you've had that, or perhaps grad school if you want to take a little look at what's going on here, or if you're a researcher in an area and you need to do a little thermodynamics, then you want to make sure that you understand the rigorous underpinnings, then hopefully you'll find this course useful. And all the time, I'll try to give us some intuition. I'll try to connect with some of the stuff that we have learned way back in general chemistry or physical chemistry or thermal physics, while sticking to the level of rigor. Now, let me just say a little bit about the level of rigor. This is not the most absolutely rigorous course we could have done, because I do want to keep us talking about the ideas of what's really going on in this material, and not abstract it all the way to mathematics. And by that token, there's no way we can take thermodynamics all the way down to the level of geometry or number theory or set theory, where it's can be purely abstracted from nature and just set up as a set of rules. Nature injects itself into the rules, and from there, then we use mathematics to proceed through relations that are less intuitive to us. All right, so with that in mind, let me just go through the axioms of which we're starting with here, and hopefully that'll give you the sense of the level of the rigor that we are dealing with. So, energy and matter exist. So we're just going to say that there is a natural world and we are able to explore it. And it really comes down to energy and matter. Energy and matter are separately conserved. Now, we know that they're really one thing, according to relativity, and we can interconvert matter and energy. But in chemistry, that never happens. Nuclear chemistry, so nuclear reaction, that does happen to some degree. If we're doing thermodynamics I imagine that you'd have to think about a little bit in thermodynamics of, say, black holes. But even there, you kind of segregate things a bit. So for us, we're going to be focused primarily on conservation of energy. We won't need conservation of matter in this course. Now, these, I think, that's as rigorous as we can get in terms of still injecting things from the physical world. and not completely abstracting away from anything physical. Here's where you could have a bone to pick with me here, but I'm going to say that we're going to start here, that there exists entropy, and it's a state function. As you might have recalled from courses you've had, entropy in thermodynamics is really sort of just thrown in there because it's of critical importance, it's of fundamental importance, and it is well explored. But it only becomes satisfactorily understood in the context of statistical mechanics. And we aren't going to do that here. This is all just completely devoid of any reference to statistical mechanics. So with that, we have to inject the concept of entropy. And so we'll have a thermodynamic definition of entropy. Extensive and intensive variables. Again, you could argue with this. I'm not going to prove that extensive variables are linear in the amount of material. I think it's very clear that intensive variables, just by definition, they're not, so we don't need to really prove that. But extensive variables, we're going to take them to be linear in they're dependent on the amount of material. Okay, so two things that flow immediately from the axioms is the first law of thermodynamics, and so this will be the focus of our next lecture, our first lecture, and that says that the energy is conserved between the system and its surroundings, and so the change of the internal energy of the system is due to a change or an exchange of heat, which is Q, and work, which is W. And then entropy comes in as a definition. Thermodynamic definition of entropy is that it is the reversible heat, so only on a reversible path, divided by T. Now, we're going to need some notions that are really logic statements here. And these are mathematical and physical, but they're all kind of pretty, I think we'll be pretty comfortable with them. So the first is that we can express work in terms of a generalized force, this really fancy A here, and a generalized displacement, such that if the units of these equal energy, that's a way to talk about work. So we can talk about electrical work, which would be a voltage and a charge. We could talk about pressure volume work, like with a piston. That would be pressure and volume. A rubber sheet expanding, that would be surface tension and area. So we can talk about work as a generalized force, generalized displacement, and all work on paper anyway is interconvertible. Now, of course, in real life, there's always inefficiency. You can never get 100% conversion of, say, electrical work into mechanical work. But on paper, you can. And so we are saying that we can build up the theory by lumping all the work together. And so if you weren't told that when you took a course in physical chemistry or thermophysics, and you were wondering, okay, we did all this thermodynamics with a piston and pressure volume work, it seems like that's a pretty limited case. This expands it then. When we're not worried about the particulars, we can lay down the laws and establish the theory of thermodynamics just thinking about the piston. And the piston's a really good system, and so that's what's always done in all of the books. But then when it comes to actually solving problems in thermodynamics, then you have to break out what the individual work is. But for our purposes, we're not doing that, right? We're laying just down this rigorous theory. We're not going to do any applications, and so we, for our purposes, we can collect all work as pressure volume work, and we're gonna segregate out material motion work. So this is written in terms of the chemical potential and the number of moles. The other notion we have is that state functions are path independent, and that's I think pretty clear that the functions of state, what describes the system, where it is now, they're independent of how it got there. So if I'm talking about the volume of a beaker of benzene and it's sitting on the lab bench, it doesn't matter if I took it from the refrigerator or if I took it from a hotter room and it came to the temperature of our room on the lab bench. Its volume is what it is. Its entropy is what it is. Its temperature is what it is. It doesn't matter the history of how it got there. So that's those are state functions. They're path independent. Now we will not. we'll go through path independence, but we will not rigorously define path independence. So in terms of the rigor here, when we can connect very readily to a fully fleshed out mathematical field, then we won't go deep into that rabbit hole. So path independence is very nicely taken care of in the theory of complex functions, but we're not gonna go that far. We're just gonna state this notion. Energy is on a relative scale, and then everything else is on an absolute scale. So temperature, pressure, well, everything else that doesn't depend on energy, temperature, pressure, volume, that's a V, not a U, and number of moles on an absolute scale. Chemical potential, free energy, enthalpy, those all involve energy, so they are on a relative scale. And then the third law, which we're not going to talk about at all, the third law, the key important idea of the third law is that it establishes an absolute entropy. So the second law just talks about entropy. The third law establishes entropy as a, I should have been, it's too flippant in that the second law establishes a criteria for spontaneity in terms of entropy. The third law puts entropy on an absolute scale. So this means we can define the zero of energy any way we want. The absolute entropy is determined by absolute zero. Absolute volume is determined by the number, can't go to negative volume, so on. And then of the paths, okay, we talked about path independent. Of the paths, there are reversible paths. That's when the system is always in equilibrium at the infinitesimal level. So under those conditions, the pressure of the system is always equal to the external pressure. And work is the reversible work along a reversible path is the maximum work. And that's related to free energy. Free energy is the energy available to do work, not the energy that is doing work, but the energy available to do work. So the maximum is Helmholtz free energy here. All right, let's talk about the prerequisites. So you should have calculus. I think that you probably won't get as much out of the course if you haven't had calculus. You should have had thermodynamics, I think, at the level beyond just Gen Chem or general physics. So if you had a course in physical chemistry that went over thermodynamics, that should be plenty good. So some kind of first pass at thermodynamics, even if you've forgotten a lot of it. So you should remember things like the reaction quotient, equilibrium constant. That, even at the general chemistry level, will be enough. Chemical potential, which is never talked about in general chemistry. So you should know that. Activity. You don't have to know a lot about activity, so you don't have to have taken an analytical chemistry course where you have to be really careful with the activity. You just have to be comfortable with the fact that how a chemical behaves, how a species behaves at its particular conditions is given to us by the activity, and we often approximate the activity as concentration or partial pressure, which is what's done in general chemistry, but mainly just how it's related to the reaction quotient and the equilibrium constant. And then we need to know about enthalpy. Should be very comfortable with enthalpy and free energies, Gibbs free energy and Helmholtz free energy. We will, the central player will be internal energy. So that's the other, well, we've talked about that up here. So internal energy, entropy, and then these auxiliary functions. We will derive them. We will, we will talk about them. So if you you don't have to be like, oh, sharp. Right now, you could tell me everything about that, but just that you feel like these ring a bell, these terms ring a bell. They're not completely new to you. Then I think you should be in good shape and be able to get a fair bit out of this mini course. So as I said, this will be I think 6 lectures. Yep, 6 lectures after this one, and we'll just sort of systematically build our way with a focus on chemistry.